Okay, welcome. So what we're going to be doing today is we're going to be moving on to the fluids topic, and we're going to be discussing a lesson on fluid pressure today. All right, so let's go ahead and jump into that. Notes are shared. Okay, first thing I want to discuss is the definition of a fluid. Now, a lot of people, when they hear the term fluid, what they think is liquid. Really, what it is liquid or gas. Um, what a fluid generally means is it means that it engages in fluid flow. And basically what this means is it's matter that can rearrange its shape in order to fill the container. And when it moves, it rearranges its shape to to move in whatever way possible. So its motion and its equilibrium have to take into account the fact that the matter can effectively change shape very easily. In fact, it changes shape in response to forces, and this has some various implications in terms of the different kinds of fluid flow and the different kinds of fluid behavior. Now, in general, liquids and gases are different. In the context of fluid, what we generally mean when we say a liquid, this is an incompressible fluid. And you might have a sense of what that means. Basically, it means that you can't exert forces on this fluid and change its volume. Okay. So if you think about it this way, well, I'll cover gas as well. Gas, this is generally it's not one for one. Some liquids are somewhat compressible, like you can do a little bit of that. But gases in general can be highly compressed, liquids cannot. Okay. So you think about it this way, like you have say like a basketball or something. You can kind of keep pumping air into that basketball. And basically what you're doing is you're compressing the air to pump it into the basketball. Now, if you've ever completely overinflated a ball, you know that eventually you can rip the ball apart, and that can't happen. Now, if you tried to force water into that ball, you would basically fill up the ball until it was full of water, and you would not need very much more water to completely rip the ball apart. The idea is that, you can force more air into the same volume. That's what it means to compress it. You can't really do that with water, okay? And that's in general, the distinction between liquids and gases in terms of in fluid terms. When you think about liquids and gases, you probably have like a better idea. Liquids, they're generally heavier than air. They're not generally heavier. They are heavier than air, and so they sit below. Generally, they sit below any gases. Now, you can have some very dense gases, which can be interesting, but in general, liquids are more dense than gases, and we'll get to density in just a moment. Okay. So again, the idea is that both of these things flow, and the whole idea behind flow is that the shape of the material can rearrange to move, and I'm going to state this broadly, to equilibrium. Okay. The idea here is that equilibrium is that if we have a solid object, its shape can't rearrange. So it'll just sit there. Like, you imagine your computer, it just sits there on the desk. It keeps its shape. It's got forces that are on it, but the forces holding the shape to itself are stronger than anything that wants to, rip the laptop apart, gravity or normal. In the case of a liquid, that's not true. If you pour a liquid out of a cup, it doesn't stay the same shape as the cup. Gravity basically flattens it. It flattens it all out. Same thing occurs with gases. You can see this. Sometimes you can see this if you go to like the freezer aisle in a store, and you can see like the cold air will be kind of misty. You open the freezer, and what will happen is you get a whole bunch of the cold air that is actually visualizable, and basically that cold air will just flatten out along the ground. Okay, so again, changing its shape in order to reach some equilibrium point. This is what fluids can do. And as a consequence, a lot of the physical laws we learned about motion of solid objects we need to sort of rethink them and reconceptualize them in terms of something that works for fluids. Now, we're going to need to define some new concepts in that are going to keep coming up in fluids. So that's largely what is going to happen today. Now, the first one is density, and perhaps you may be familiar with this, but because a particular fluid can always change its shape, a lot of times it makes more sense to refer to the density of the fluid rather than the mass of the particular fluid, okay? Because this fluid can change its shape, it can break apart, it can do whatever. And the point is that the density is going to stay constant, even if, you know, the fluid changes shape, spreads out a lot. Or sometimes it will, sometimes it won't. That's again. But what we can do is we can characterize the density of a fluid in a way that it's a little bit more difficult to do for a mass. Because a solid object, the matter coheres together, we can talk about the mass of that object. We can also talk about the density of that object, but the mass tends to be somewhat more effective. Density is mass per unit volume. And we talked a bit about this when we talked about drag. The density of the fluid came up. Drag is a force that enters into fluid flow, really. And we discussed it in the context of mechanics, but really people started analyzing drag once they understood a little bit more about fluid mechanics instead. So mass per unit volume, the symbol is this kind of weird looking P. That is the Greek symbol rho. So a lot of times you'll have a subscript because the subscript will indicate what it's the density of, but in general, it's just this kind of weird looking P. You'll see me kind of write it like that just to kind of indicate that it's not exactly a P. I'll try and put a tail on it. And it just is the mass. And then that is not velocity, that is volume. It is supposed to be a capital V. Capital V's and lowercase v's look identical, unless you're looking at a textbook, which is nice. It's one of the things you can tell by a textbook. But if you're writing it, a lot of times they look identical. But this is volume. So mass and volume. Now the SI units are kilograms per meter cubed. Now, this is SI. And I will say, one of the things you need to be aware of that when it comes to density is that a lot of times you won't be given SI, okay? So when you want to start connecting density to other calculations, the reason is a lot of times a meter cubed is a very large volume of something. We particularly in the context of chemistry, that didn't come up a lot. You weren't dealing with entire meters cubed. Like if you imagine a meter cubed, it's a cube with a meter on each edge. That's a pretty big volume. And we can deal with that much, but it turns out a centimeter cubed is more common. Now, a centimeter cubed is 1 milliliter. I'll put this off to the side. 1 centimeter cubed equals 1 milliliter. That is a conversion to know. The other another conversion common to know is that 1 meter cubed is equal to 1 million centimeters cubed, or 1 times 10 to the 6th centimeters cubed. And you're like, wait a minute. There's 100 centimeters per meter. Well, that's true. But if you imagine, if you have that meter cube on each edge and you divide each one of those edges into 100, basically the number of centimeters cubed that's going to fit into that giant cube, you're going to have 100 along one edge, 100 along another edge. That means you'll have 100 times 100 just on the bottom level. And 100 times 100 is 10,000. So just on the bottom level, you have 10,000 centimeters cubed. But then you need a stack of 100 of those levels. So basically what I'm asking you to visualize is kind of like a cube. I'll just divide this one into 3, so you can see kind of what goes on, how it scales. Maybe you're like, nah, I already got this. But if we divide each one of these sides into 3, what I hope you will see, that's not quite right. What I hope you'll see is that basically what is going to go on is that on each one of these edges, you are going to have you can kind of, it's not very great, but you can kind of see on the top what you have is 9 nine tiny cubes on the top. Now we've just divided each one of the sides into 3. So 9 tiny cubes on the top. And then you have another level. You have 3 levels of that. So you have 9 plus 9 plus 9. So that's 9 times 3, which is 3 cubed. Another simpler way to think about that is that 1 meter cubed, you can think about this as 1 centimeter, and you cube it. And when you do that, you have to cube the 100 as well. Okay, so that's where you get that. 100 cubed is just 1 million. So that's a conversion factor to know. All right. One density that I want you to be aware of, a very common density. This is actually how, I think this is how a gram was ultimately decided, because water is so common. I think that a meter was decided another way. It's like some fraction of the distance from Paris to the North Pole or something. But a gram was decided in such a way that the density of water is equal to 1 gram per centimeter cubed. Now, one thing I want to indicate this, so 1 gram per centimeter cubed. That's the density of water. And water, just make that clear. Now, another conversion factor to know, since you're given things in grams per centimeters cubed, I'm going to convert this to kilograms per meter cubed, okay? Because kilograms per meter cubed is the SI. And again, if you want to use, in a lot of SI applications, if you want to use density, you got to convert to that. So know how to do it. And it's not that hard. So I just want to convince you of what's going on here. So we'll do this conversion first. We have 1 million centimeters cubed per meter cubed. So basically this would be 1 million grams per meter cubed, but we also have a kilogram is equal to 1,000 grams. So we can change that as well. And basically this 1,000 cancels out with 3 of those zeros right there. And the grams cancel, the centimeters cubed. Oh, whoops, I canceled the meter cubed. I did not want to do that. The centimeters cubed cancel with the centimeters cubed. And then we just have kilograms and meters cubed. And that would just be 1,000 kilograms per meter cubed. So the idea here is that if you are given something in grams per centimeters cubed, then what you do is you multiply that by 1,000, and that will give you kilograms per meter cubed. Okay, and you can kind of imagine this, like if you imagine like what a centimeter cubed is, just you can even draw it on your paper. Draw a cube a centimeter on edge, and you can imagine you fill that up with water. Okay, that's 1 gram. Well, if you were to take one of those, a meter cube on a side, and you were to visualize that, maybe you do it with a meter stick, and you fill that up with water, that would be pretty heavy. That would be way heavier than you could lift. Okay, and the idea is that cube of water that's 1 meter on each edge, that has a mass of 1,000 kilograms. It's called a short ton. It's about 2,200 pounds. No, sorry, that's a metric ton. A short ton is the other one. Short ton is an imperial ton, which is 2,000 pounds. Okay. So in any event, that's the conversion factor. Now, one other thing to talk about in this context is something called specific gravity. And this doesn't really have a symbol. It will sometimes be given as just SG. And really, it's a dimensionless way of expressing a dimensionless way of expressing density. And basically what it is, the specific gravity of any fluid or any object really, it's just equal. So this, say the specific gravity of X, where X could be anything. It's equal to the density of X divided by the density of water. Okay, so the nice thing about this is that basically the specific gravity is just the density of the material in grams per centimeters cubed with no units. Okay, so you can always find a specific gravity, and basically, again, what all specific gravity is, it's a comparison of an object's density to the density of water. Now, the reason this is often useful is, and we'll get to this, is knowing knowing the specific gravity, knowing how it compares to water will actually tell you if something floats. I don't think this is going to come up much in the problems we're going to do, but it's worth knowing. It's worth having here, so I'm going to include it. All right. Next one I want to talk about, next concept I want to talk about is pressure. And pressure has a number of different ideas behind it. Not a number of different ideas, but it's first relevant towards fluids, and then we can actually start thinking about it in terms of as a general application of forces. So when I introduce the concept of pressure, you've probably seen measurements of pressure before, but you might not have a very clear definition of what it is. The way I like to think about it, it is the strength of the push from a fluid. Okay. Now, this has certain implications this has certain implications that are a little bit different than the strength of a push from an object, okay? And the idea is that if you were to have something like a water tank, just draw a big water tank, it's full of water, and we'll fill it in with water like so. The idea here is that this water is pushing outward against this tank because this thing can rearrange itself. And there's nothing like if this was a block of ice, the ice would not be really pushing against the sides of the tank. Like it might be depending on how it was frozen, but in general, if you just put a block of ice this normal size inside this tank, yeah, the ice would be pushing down, but it wouldn't be pushing on the sides of the tank because it would be held together internally. Now, water is different. Water not only pushes down, but it pushes in all directions. So the idea here is you get these pushes out in this direction, and those can be thought of as forces. But the fact that water, and then you could, it pushes on all the edges of the tank as well. The idea, so push from the fluid. The idea there is that we want to have a way to quantify the strength of this fluid, and we do that via pressure. Okay, so that is the idea. Now, ultimately, there's a couple of characteristics. Is that pressure, and in particular fluid pressure, pushes in all directions. Okay, this is one thing that ends up being pretty important. It's the fact that this is the case, we'll get into this in a little bit, but the fact that this is the case is one of the reasons why, like a person, if this tank was like, I don't know, 30 feet high, a person could swim to the bottom and still be under most of the weight of the water, and they'd more or less be fine. Like if you've ever, ever swum down to the bottom of something fairly deep, you do feel a little bit different. Like you can feel it pushing, on your on like your ears and anywhere there's air in your body, you can kind of feel it pushing there. But it's not gonna kill you to swim 30 feet down. However, if you took this person outside the water tank and put them underneath the water tank, that would crush them. Okay, that would completely obliterate them. All right, so a big part of that is even though you are still under most of the weight of that water, it's not just the additional weight of the tank. Even though you're under most of the weight of the water, the fact that the pressure is pushing in all directions is helping you get crushed from all the weight of the water above you. All right. Now, again, it does still have an effect, and we'll talk about that, but that's kind of what's going on. Now, the other thing is that so it's the strength of the push of the fluid. It pushes in all directions. What this means fundamentally is that pressure is a scalar. And the idea here is we think about it, okay, it's a force and force has direction, but what pressure is doing, it's related, it's the only thing that generates pressure is like a force perpendicular to an area. So basically, we define both the area of the direction of the force and basically direction perpendicular to the area, and they have to be in the same direction, which is how it becomes a scalar. Now, how that works out in vector math, that's what we call a dot product. I wouldn't worry too much about that. Just know that pressure is a scalar. Now, a big part of this was, okay, we want to relate pressure to force. Okay, so what is, if we have some fairly reliable ways to increase pressure, like we can, we can increase the depth of a water tank. That increases the pressure down at the bottom. We know that. We'll get to that in a minute. But the thing is how does pressure relate to force? And the idea here is that force, we'll just say, for a constant pressure, I'm going to do this in bold because it's worth doing. For a constant pressure, force increases directly with area. Okay, so the way you can think about this is like if you have, like this 30-foot water tank and you had like a little pinhole in it, you could fairly easily exert the force with your hand to plug that pinhole, even with all that water above it. Like you'd have a massive amount of water that you're basically holding in with your thumb. But as long as it's a pinhole, you don't actually need that much force to do it. However, if that hole was like a door the size of a meter, there'd be no way you could hold that back. It would be pushing on you way too hard. Like you could lean into that with all of your strength and you wouldn't be able to hold that back if it was under 30 feet of water. Okay, so the idea there is that force increases directly with area. And so this brings us to the equation that the pressure is equal to force per unit area. And the idea is if this can be arranged to force equals area times pressure. So as area increases, it increases directly with force if pressure was constant. Okay. Now what this means is pressure can be, you can find the pressure of any force, and you can increase pressure not by just increasing force, but by decreasing area. So this is something worth noting. So pressure can be calculated for any force. And this is, if you think back to when we were talking about stresses and strains, this was basically a pressure measurement on particular objects. So pressure can be calculated for any force, and again, it's just the pressure is equal to the force exerted divided by the area of exertion. Okay. So the idea here is that if you have, just for an example, if you have like we'll do a tall box, kind of like so. Like so. And then it has a mass of M, but then you put the box on its side. Oh, whoops. That's not what I wanted to do. And like so. And there we go. Then you put the box on its side, and they both have the same mass. This has more pressure, and the reason is that it's it's the same mass, so the same weight, but exerted over a smaller area, if it's sitting on a table. And the idea is that this one would have less pressure. The idea is that more pressure is actually more likely to break things. Okay, so there you'll see a couple of examples like that. Now, when it comes to the units of pressure, okay, pressure can be measured in many different ways. Units of pressure. The SI unit is just remember, the formula is pressure equals F over A. So the SI unit is newtons per meter squared. And this is actually we derive this, we call this the symbol is PA. That is for Pascal. So so the SI unit of pressure is Pascal, but there are several other units of pressure. One of them is millimeters of mercury. So you might see this, millimeters Hg. Now, the reason that millimeters of Hg is used is because this was actually one of the first ways that pressure was ever measured, and it was atmospheric pressure. I think it might have been Pascal who did this. Either Pascal or Torricelli, I don't remember. I think it was Pascal. But anyway, what he did is he managed to get a cylinder full of mercury, and then he kept it sealed, and he dumped it over in such that the top was in a puddle of mercury. And what he saw is that some of the mercury would fall down, but it wouldn't fall down all the way. Basically, what was going on is the air pressure from outside was holding the mercury up. So the idea here is that, well, if you have this thing and you have, so this is all mercury, Hg, and then you have a little tube going up like so. I'll color this in purple. Mercury isn't purple, it's silver. If you've ever seen mercury, it's kind of cool. But the idea here is that what you would have is it would stop at some level, okay? And in here, this would not be air, this would be a vacuum. And basically, he could ensure that was vacuum just by having the tube filled initially and not letting any air in, okay? So if you ever get a chance to, you can do this, you can see this effect with water. You can't actually see it empty with water because basically it's quite difficult. But if you're washing dishes sometime, you fill a glass up with water and then keep the glass underneath the water and then start to keep the lip of the glass underneath and start to lift the bottom out. What you'll see is that the water will stay in the glass, okay? Kind of like this. Now it will fall once you break it and you allow air in, but before you allow air in, the water will just stay in the glass. It's kind of an interesting little phenomenon. Okay. And the idea here is basically what he saw that this could be used to measure pressure. Now another thing he saw is that on average at sea level, what he had 760 millimeters of mercury on an average day. And if it was less than that, he said, okay, the pressure has gone down. If it was more than that, he said, okay, the pressure has gone up. So this was a very common way of measuring, particularly atmospheric pressure initially. So that's where millimeters of mercury come from. The other one I just gave there is atmospheres. And so atmospheres. And the way this is abbreviated is ATM. Another common way. Again, generally, this is measuring gas pressure or atmospheric pressure. But you can do it. You can express other fluid pressures in atmospheres as well. The idea here is that, and I'll give you a straight conversion between all of these. 1 atmosphere is equal to 760 millimeters of mercury, and that is equal to 101.3 kilopascals. Now, a kilopascal is, again, just write this. It would be 101,300 pascals. I think it's like 350, but whatever. 4 significant figures is enough. Okay, so this is the unit conversion that you will need to know, and you will see these things come up. Okay, all 3 of these units will come up when it comes to pressure. All right. Now, one other thing I wanted to talk about is the fluid pressure derivation. Okay, so fluid pressure. And basically what this comes from is it's going to be the weight of a fluid per unit area. Okay. So the very simple way to do this is if you have, just a tank of whatever fluid. We could say it's water, but I'm just going to say it's just a general fluid right here, a tank of this. And the idea is that this tank of fluid has some fluid pressure that it's exerting. And, basically, again, if you were to poke a hole in the tank, fluid would get forced out, and that's because the fluid has a pressure. Now, we'll say that the fluid just has a density. We'll just call that density of the fluid. And then we'll say, this distance right here will be height. And if we want to know the pressure at the bottom, so pressure bottom, basically what we're going to do is we're going to take a little, I'll do this in red. We're going to take a little patch that has an area of A down at the bottom. So area equals A. And what we're going to do is we're going to figure out the weight of the fluid above it. Okay, so the weight of the fluid above it. So we want to know F sub G of this fluid, of this column of fluid in red, okay, that I've drawn there. So that's what we want to know. We want to know the force of gravity. We're going to divide that by A. All right, well, we can start doing this derivation. So we can go ahead and we can say, okay, the force of gravity of the fluid is just going to be the mass of the fluid times G. Okay, cool. But we don't know the mass of the fluid. We do know the density of the fluid. So we can kind of go from there. But reminding ourselves that mass divided by volume equals density. This is going to mean that mass is equal to density times volume. So we can make that substitution. So we can, instead of having mass of the fluid, we can convert this to the density of the fluid times the volume of the fluid times G. Now, what we can do, one other thing we can do is we can realize that the volume of this fluid is just going to be the area of that patch down at the bottom. So I'll rewrite that in red so we know where that comes from. So it's going to be the area of that patch. And then you're going to multiply that times the height. Okay. Whatever that patch is, like it could be a circle, could be a square. It's just a sample patch. And the whole idea here is that we'll actually see that it cancels. Okay. That's why we can use any area that we want. So now the force of gravity of that column of red fluid that I've drawn, instead of volume, that should have been an F there. We have the density of the fluid times the area times the height times G. Okay, fine. Now what we want to do is we want to know the pressure at the bottom, and I'm just going to call this the fluid pressure. It's the force of gravity of the fluid divided by the area of that patch that we just talked about. Okay, so once we substitute in, we get the density of the fluid times G times H, and I'm rearranging a little bit. Hopefully you forgive me. And then we have the area of the patch in the numerator and the area of the patch in the denominator. Those two will cancel. And we end up with a very simple formula for fluid pressure. The fluid pressure is equal to the density of the fluid times G times H. Okay, so this is the fluid pressure formula. Now, I will say this does make an assumption. It makes an assumption that the density is constant all the way down. Like when we calculated that mass, we had to assume that the density is constant. It works well for this assumption works well for liquids, not as well for gases. And the reason is that a gas is more dense down at the bottom. So the idea, if you think about the Earth's atmosphere, the gas is more dense at sea level. The atmospheric gas is more dense at sea level than it is at elevation. Okay, so that's something worth keeping in mind. Now, last thing I wanted to discuss here in this lecture, this is going to be gauge pressure versus absolute pressure. Now, what most pressure devices do is they measure a force, okay? They measure a force per unit area. So the way you could think about this is you could think about, all right, basically, I'll just do it. Just like say it's a scale. And what we're doing, let's just say we've got, fluid in here, whatever. So we have some fluid that we're measuring here. Um, and we want to know, could be air, could be anything. We want to know the pressure. So pressure is equal to force per unit area. Basically and then this thing right here would be a scale. That scale would measure the force. Okay, it would measure the force, and then it would have a constant area that wouldn't change. So the scale measures the force. Area is constant. So basically, you can convert directly from the force to the pressure. All right, that's the idea. But the issue with most tools for measuring pressure is what you have. I'll do this in blue. What you have out here is air. And the idea is that what you have down below here is you have pressure from the air exerting an upward force. Okay. And it doesn't matter if you do it up or down, because the air pressure exerts forces in all directions. Okay. So the idea here is that the pressure measured, that pressure inside, that measured pressure, does not account for atmospheric pressure. Okay. And the reason why is that if that scale, if that the pressure of that purple fluid, if that is exactly equal to atmospheric pressure, that scale is going to read nothing. Okay, because it's going to be balanced on both sides. All right, that's the idea. So the scale is only going to measure things above atmospheric pressure, possibly below. Like if the scale can read negative numbers, it can measure it can measure it can measure things below atmospheric pressure. But the idea here is that the pressure of the scale equals 0 if P equals P atmospheric. Okay. And that's the idea. So gauge pressure, we would call this gauge pressure actually. So P gauge equals 0 if the real pressure is equal to atmospheric pressure. Okay. So the idea behind these formulas is that if you want to find the absolute pressure, you take the gauge pressure, and gauge pressure, this is how most tools measure gauge pressure. You could get a gauge to measure absolute pressure, but you'd have to have vacuum on the other side. Like you'd have to make sure that atmospheric pressure wasn't exerting a force on the other side. So P absolute is P gauge plus P atmospheric, and I'll do that in bold as well. We'll box that. So P absolute pressure equals P gauge plus P atmospheric. And again, P atmospheric is generally 1 atmosphere. So we'll indicate that equals approximately 1 atmosphere. And again, you can look up at the conversion factor. Now, P atmospheric will change depending on where you are. That's what can make this tricky. Okay. So if you've ever had the experience of you drive to, you fill your tires up, we're at about 4,000 feet here, I think. You fill your tires up to a particular pressure, you drive down to sea level, and there's less pressure in the tires. It's not because you necessarily lost air, though you might have. Basically, what happened is that the what you are measuring your pressure against was lower. Your atmospheric pressure was lower at higher elevation than it is at sea level. Another way you can think about that, the atmospheric pressure is pushing in on your tires a little bit more. So when you measure that against a gauge, it seems like there's less pressure in your tires because it's closer to atmospheric pressure. Now your tires would still be inflated. But that's the idea behind atmospheric and gauge pressure. Okay, so next lecture, we will get into Pascal's principle, and we will basically go from there. So thank you for joining me today. I will see you in the next lecture.